A couple class periods ago, we talked about a wire loop. So we had this loop of wire, and we had current flowing in this wire, and the text goes into great detail about how to derive the magnetic field along the axis of this loop. Okay, and in our videos, we pointed out how you can go from that wire loop down to a dipole. And we wrote down the magnetic field along the axis of a dipole. Today I want to focus on dipoles and some interesting effects for them. If we were to look at a loop straight from the side, so this is a piece of copper wire that's connected, and so I'm going to do a cross section here, cut it in half, and let's say the current's flowing out of the top and then flowing in at the bottom. So the dot means the current's flowing out at you, and the cross means the current's flowing in. So it's flowing out of the page, out of the page, into the page, out of the page, into the page, like that. Okay. Now we can use our right-hand rule to figure out along this axis what the direction of the magnetic field is. And I'm going to emphasize the curly way. Okay. So the current right now is curling, and your hands are curling. Your thumb is straight. And so you can curl your hands in the direction of the current, so out of the page at the top, and your thumb will indicate the direction of the magnetic field in the middle of that loop. Okay, so curling thing, straight magnetic field. All right, and so we know that the field is going to be pointing like this, and it'll get smaller with distance as you go away. Okay, so what I want to point out in this video is that this acts a lot like a bar magnet. There's very little difference between that and if I have a really small bar magnet. Okay, I'm going to draw, and here's my north and my south. Okay, so every magnet has a north pole and a south pole. And we know that bar magnets attract south to north. Okay, so if I have another bar magnet right here, if I put the south pole near the north, they'll snap together. If I put the north pole near the north pole, then it'll fly apart or try to flip around and snap together. Okay? And so this is acting a heck of a lot like this. The magnetic field for a bar magnet looks the same. And in fact, the beauty of this is that the way we calculated the magnetic field for a dipole, we focused not necessarily on how big it is, but its dipole moment, it's mu. And that is the essence of how we can connect electrical currents with bar magnets or physical magnets. Okay? The molecules inside a bar magnet act like a bunch of little dipoles. And so they have this little dipole moment. So this has a dipole moment. It's in the center, but I'm going to draw it. It's got a direction. The direction points in the direction of the magnetic field that it causes. It points from south to north pole. So these teeny bar magnets can have a dipole moment, okay? Which means they can interact with each other just like little bar magnets. So if I put another current loop, and let's just go ahead and put them in the same direction. The current's flowing out at the top and flowing in at the bottom. Okay? Well, I know the mu is going to point this way, which means this is the north and this is the south. We've got our mu pointing this way. This is the north and this is the south, which means if what I just said is true, these should feel an attractive force because they have north and south close together, so they should pull together. Okay, now let's try and show that and make that clear from our basic rule of F equals I dl cross B, where this B is from the source. So I'm going to call this one the source, and this is the current of the test. I'm going to call this one the test. Okay? So in order to find that, let's focus on just two places, and then we can extrapolate all along this loop. Remembering, this is a two-dimensional loop, so if I were to draw it in kind of a three-quarters view, we'd see it kind of like this. We're looking at straight on the sides. All right, so if I think about the magnetic fields of a current loop, if I were to draw one here, they kind of look like that. Okay, and right down the center, they're straight out and straight in. Okay, and these rings just go forever, continue forever. And so if I were to see what's the field up here, well, that's probably a field line that's coming out like that, and at that point, the tangent to that field line is that way. So this would be B source, and we could do something similarly, symmetrically. We have B source going that way. All right. Okay, well, with that being the case, and the current is flowing out here and in here, what is the direction of the force, at least due to those two pieces of the current? Okay, the top piece and the bottom piece of this loop. Let's use our right-hand rule thingamajigger. Okay, so we're going to have, again, it's green to, is velocity to magnetic field gives you the force. That's what we're using the force law, so it's IL cross B. So I cross B gives you force. Okay, so our current is out of the page at the top, and the B field points at some angle like that, which means my force is going to point like this. All right. Now we can do something similar for the bottom. The current is into the page. Okay, so my green's pointing into the page. The B field points something like that, which means my force points like that, as I saw with my red arrow here. Okay? So, if these are, the field, if this is symmetric, then the fields are the same, the current's the same, and if I choose, the same amount of length there that I'm analyzing, these forces are identical and pointing those directions. Which, if that's the case, I can break them into components, one parallel to the axis of the loops and one perpendicular, and we can see that these cancel and we get a net attractive force. So we do get an attractive force. That would be F net. Okay. So by this rule, we are able to conclude how physical magnets work, recognizing that the molecules, atoms inside physical magnets act like little current loops based on their fundamental physical properties. Okay?